Hi, my name is Dr. Kyle Keane. I'm going to talk about how we use Wolfram language inside of MIT's undergraduate curriculum in multiple departments. For those of you who are here last 30 minutes, I am still Kyle Keane. For those of you who are new, I am Kyle Keane, still. I teach and do lots of stuff at MIT, and I am an absolute Wolfram lover, I guess I would just call it. So, yes, the things I'm going to talk about are just what we have been doing at MIT to bring... Oh, my scroll bar doesn't show up. All right. What I've been doing at MIT to try to bring coding and computational thinking into the curriculum. I have this really great position where I can get hired by other departments to teach classes, so I'm not really stuck in my department. So I've worked with physics and computer science and material science, and I have some grants out to hopefully break into the humanities. So I get to kind of be this all over the place person, which suits my personality well. So we'll talk about I have a PhD in physics. I learned coding. I opened my first computer my sophomore year in college, and Mathematica was on it. And I learned coding inside of physics. So this is like the heart and soul of what drives me. So I love that I get to be part of the MIT Intro Physics class. And then my home department right now is material science and engineering. And what they hired me for was to bring coding throughout their curriculum, as well as have a designated class about computational methods that I'm helping Professor Craig Carter, who some of you may know. He's a long-term Wolfram user. And then the online physics course, I'll talk a bit more about the content that we actually throw into these online courses and the experiment that we're running to understand if it's actually valuable to put widgets or coding, or if we should just let students do paper and pencil math, which I don't personally believe, but I would love to see data to support. So we will begin with there's a few things that I believe when teaching with computational methods inside of classes. You can scaffold students up and then fade how much support you're giving them. So students have some concept of material science. They understand diffusion as a random walk on a lattice. So if you walk around on a lattice, at some point you end up some distance away from where you start it. And you can plot, if you do that a bunch of different times, what the expected position, the distance away from the center is. And so you can show students how to do that in one dimension. And the code is very simple. It's really kind of approachable. And you just have them stepping back and forth on a number line. And at some point, the integer ends up different than it started. And you look at the distance by subtracting. And you can get a nice plot. So by almost completing this entire thing, you've pretty much modeled how to solve the problem. And my favorite thing in Wolfram is how simple it is to move 1D to 2D to ND. As soon as you do 2D, you're just kind of off and running, and you can just do however many dimensions you want. So by the time you show them 2 dimensions, you say, here's a vector. Here's how you describe 2 points on a lattice. They can pretty much fill in all of these gaps by moving across. And then by the end, they should essentially be able to generalize to 3 dimensions without you having provided any specific information. So this is, in general, my personal belief is how you blend computation in. This is scaffolded, fade it. The scaffolding is you have to give them something that they understand that they can build off of. The fading is you start to give them less and less explicit hand-holding. And the worked example is the fact that they actually get to see a real world problem solved. You're not just giving them some contrived example. Okay, so the 801 is our intro to physics. It's kinematics. You like throw a ball and see how it flies through the air. And I will just be hopping back and forth between notebooks to show you wait, that is the other car on. Sorry, not car in a turn. Oh, actually it is. Oh, I get to show you 2 cars on a banked curve. Cool. So this is what I said is Code Seal 2.0. So I have a whole authoring system for creating notebooks that have hidden content from students, that have some level of auto-grading, that have some level of forced scaffolding and progressive, like you can't move on to this section until you've done that section. After a lot of user testing last year, I've come back to a much simpler version of that. So there's reading, which is just a notebook with some content. The problem itself, now we're looking more like a traditional textbook where there's some reading and then there's a problem injected in the middle, but the problem is a 4-step process where they need to read. Sorry for the scrolling, it's a little bit jumpy. Read through the problem, try to solve it themselves. So this stage just got unlocked when I read through the problem, and this stage down here is locked. So I can't see the solution or take a brain break. This was the very first assignment, so we just gave them some silly code. So first they need to come and try some code themselves. We give them some little indication of, of everything that's inside of these little light bulb cells are the things that will actually be graded. So there was a lot of confusion in the last version where they didn't know what was being graded. Students are disturbingly used to typing an answer into a box and not used to sharing a whole narrative. And so we are now giving them a box, and I'm going to slowly try to get them back out into feeling like expressive creatures that can share their thoughts. But this is my moment to be on a soapbox. I'm sorry. All right, so once they lock in that solution, it saves it in the file. They can't edit it anymore. It saves a little hash of it, so if they do try to cheat, we can find out. It hasn't been an issue. And once they do that, then this stage has become unlocked where they can see, normally this would be a prototypical solution from the instructor. Because in this one, we already gave them everything they needed. I gave them something that might entertain them, hopefully, which is a picture of a cat. So normally I would show them some more detail of how to solve the problem, but in this one we had already solved it. They just needed to take the code and apply it for themselves. And then important to me is that they then, when they submitted their answer and then viewed the solution, they get another copy of their solution down here where they should make edits. So either from taking a break or from seeing new content that the teacher has given them, I hope that they have some level of reflection and go back and edit their work. So this is the iterative process that I try to enforce through these notebooks, which is get a problem, try it yourself, see a solution right then and there, see if you can incorporate any of those changes into your own solution. And I don't know, I think it has been fairly successful so far. Oh yeah, no, I'm going to skip on that one. This is, oh no, click the wrong button. I'm looking forward to presenter tools being keyboard driven. So this is, you've all seen widgets, and I didn't want to show you another widget because you'll just see infinite widgets at this conference. So in 802, in the electricity and magnetism, we have things like wires wrapped around electric fields and showing magnetic fields that emerge as you move a piece of a magnet through a wire and showing the current and all these little widgety things that you've seen. So I won't use too much time about that. Instead, I will get on my soapbox about computational essays. So I mentioned students typing things in boxes and how this bothers me, because I feel like we need not just students who can type things in boxes, but ones who can express themselves. So in the material science course that I teach, we are forcing students to provide whole narratives. So code, text, images, everything needs to come together in some coherent way. We don't want students to just think that because they found, a number that they actually solved and understood the problem. So the way that we are accomplishing that is having students turn in things like this. We ask them, what is the partition function? And they need to provide text explanation, math, some code, some type of explanation of what the code is doing and why they feel that it's validly representing what the partition function is. And this, to me, is what an actual student submission should look like. I will admit fully that I spend hours and hours grading these. So if you're looking for automated grading, this is not the way to go because you can't grade something this complex, but I'm okay with that. Because this allows them to actually represent and express all of these different things, scientific reasoning, computational thinking, and until you give them a place where they can integrate all of these skills, they're going to be separate, disparate things. So I'm a huge fan of the whole computational essay movement. And that's my soapbox about that. So I feel like this little button is skipping things, but maybe it's, oh, it is. It's totally skipping things. Oh, did I click the furthest one? Oh my gosh, all right. I'm skipping things. All right, so, right. So the next thing I will share is inside of our material science course, we do something like a flipped classroom. So we have students who have, they show up to class and they work in teams of 2 or 3, and they work through teamwork projects. I'm a huge fan of collaborative learning. I think that that's a really important thing that we need to allow students to have chances to do, which is work with others. And so inside of my notebook, I give them some coding resources, some Wikipedia resources, online courses that have stuff, and then I specifically, our purpose in the class is to take math and show them where this math is going to show up in the rest of their curriculum. So I align activities with their future classes and say, okay, in 3012, you're going to be talking about, and 3012 is about thermodynamics and structure of materials. You're going to be talking about entropy. And so I'm going to give them some amount of information about entropy, let them visualize it, show them how to compute it. They're doing some nice infinite precision stuff. They can find derivatives of entropy. They can find limits. They can do plots of discretized ideal entropy, which is kind of a normalized thing. And so now I'm showing them inside of the actual notebook, like, you learned about entropy, here's how you actually compute it inside of a Mathematica environment. And then there's scattered throughout the whole notebook these little things. So there's this tendency when you're teaching coding, students will get with their laptop and they'll just stay there. And so if you have a notebook and you tell them explicitly, go through, and when you get to one of these points, you have to stop, talk to your teammate, bring over a TA. So this is the way that I enforce them to actually stay on a collaborative learning path. And you tell them, you know, reflect on this thing, talk to your partner about this, pull over a TA and explain to them what this code is doing. And this is the way that we run the class. I find it much more enjoyable and engaging, and the students seem to really enjoy it as well. So yeah, that's how we use kind of notebooks as tools for collaborative learning inside of a classroom. So notebooks are very versatile things. And that's for sophomores who have never coded in material science as well. So this is not an advanced coding class. This is for people who have never coded, but there's also people in the class who are quite advanced coders. And in this collaborative way, you still get the benefits of peer instruction. And students who are already experts can teach the ones who don't know, and that reinforces learning for both of them. So there's, even if you have a highly differentiated classroom, this type of co-instruction makes that very manageable. When otherwise, if you stand up at the front of the board and lecture at people who understand, you know, really deep coding things about really simple ones, then you're going to lose this group or lose that group. So this co-instruction is my solution to a highly differentiated classroom. The other thing that we do is in that same class, we force students to take on individual projects. So their homework is you've worked with a classmate and you've learned how to code some stuff together. Now you need to go and follow this prescribed thing and try to solve this challenge. So in this one, we are trying to convince them that the curvature of an object, if you take a bubble and you push it and you squeeze it, the curvature increases the surface energy, which makes the thing want to go back to being a sphere. So we need them to figure out computationally what curvature is, how surface energy is computed from it, and how these things relate to each other. So we use a notebook. We again give them the science, like here's Wikipedia, here's some textbooks. And then I give them a 6-step thing and I say, here's your very open-ended challenge, is visualize a surface. Visualize a surface with different curvature. Find a relationship between curvature and surface energy. Use that relationship to plot and visualize surface energy. So it's very open-ended, but very clear instructions. And I give them a simple, as I said in the scaffolding, I give them a really simple one-dimensional case so they can walk through and figure out how I would do this thing if I was working in one dimension. So I generate some random data, and I use my little thing to visualize a one-dimensional solid. And then I do something like an interpolating function to find the curvature of that solid. And then I do something like a derivative or second derivative to find the actual numerical value of the curvature of that function. And then I allow them to move into 2 dimensions or 3 dimensions, or to improve the science. So I give them a really silly curvature surface energy relationship. And one thing that they can do is go improve the science behind it, or the other thing is they can generalize to multiple dimensions. So that's notebooks as individual guided assignments where they're doing that scaffolded learning process. The other thing we do is independent projects. So this was one student who became quite interested in microfluidics. So we have a template notebook for independent projects. And we tell them you have to come up with a research statement. You need to give us some resources and inspiration. So they write some stuff about their classes. They look inside of textbooks and take pictures of things inside of textbooks that they want to visualize. They find things on the demonstrations project so that they can have some code inspiration. And this is all, so these are students doing this. I tell them, you first need to give me some visuals to define what it is you want to do in a research statement. And then they can actually start to ideate their process. So they, inside of notebooks, you can easily take pictures and just plop the picture in there. So they have a fully integrated research environment where they're learning how to tackle problems that they find interesting. And so this student did a great job. Let's see. Oh, yeah, right. So I tell them to create a sandbox and don't delete anything, because I grade them on the work that they do, even if they don't accomplish their hopeful final outcome. And then they have to put together that full narrative where they're including text and math and code and visualization in order to communicate some scientific topic. So this student did, I think, a really great job of looking at if you have a fluid running through a tube and you come and squeeze the tube, then what happens to the fluid? And if you put blood rather than water into this tube, what happens? So as you stop squeezing the tube, it relaxes into this default meniscus, and as you squeeze the tube, it starts to do some interesting things because it's a viscous, non-Newtonian fluid. So this is the velocity distribution of the front edge of the fluid as it flows through. So this is a student, this is week 6 of their first coding class. And they have gotten really interested in microfluidics and chose to do an independent research project already. And they're producing these great visualizations by grabbing textbook images and demonstration code and merging the two. So that's notebooks as a structured place to help students learn computational science. And I have 4 minutes. Wait, do I have 4 minutes until I need to let everyone leave the room, or 4 minutes until questions? Oh, okay. All right. Oh, man, then you guys don't get to hear about the cool stuff. All right. I mean, I guess, so all right, I'll do a super brief one. In this online course, we are doing a 2x2 factorial design of trying to figure out if you add visual widgets, non-visual widgets, coding or non-coding into a class, into a standard physics class, do you affect physics comprehension from the beginning to the end, or spatial reasoning, or coding ability? So there's these different aspects of things that you could, in fact, improve by introducing coding. So we cohort them into 5 groups, where one just gets a standard problem that they're going to do by pencil and paper. One gets that problem plus a visual widget and some coding exercise. One gets non-visual widget and some coding. So let me show you quickly the development of those things. So this is my other car in a bank turn. So this is the original question. It was a very standard looking physics textbook question. My problem statement is very similar, but I've added some fun color, and there's actually a story every week. Mary is this character who's become a stunt driver and was a race car driver and a stunt woman and a juggler at a circus. So she's kind of out there engaging in the world. So we're cheering Mary on as she goes around a banked turn. And so everyone gets to see that picture. Two of the groups get to see an interactive version of that, where they can come and make Mary a very daring race car driver, and then look at what happens as they rotate their coordinate system, and maybe they want to consider working in this coordinate system rather than the other one, because now there's only one vector that's pointing not in the direction of the origin, or of the original, principal axes, that's the word, yes, thank you. Like, there's a physicsy thing for this. The very lame non-visual widget is kind of a calculator, but these things definitely exist, and we want to see if they actually have an impact. So we give two of the groups a non-visual widget, and then one of the groups gets some code, and they're told, hey, look, you can do rotation matrices and figure out projections of vectors, and hopefully that helps them solve it. And then another group, in order to standardize time on task, we give them a list of questions. Just hope that they reflect upon them in order to use a bit of time. Like, what happens if you increase the bank, or what if there's no friction, and things like that. So that's our experiment. You'll have to come back next year and I'll show actual numerical results of the analysis. We have 40 students in each one of the conditions. So I'm pretty excited we have sufficient data that will be able to tell you if there's an actual impact on any of these interventions inside of a standard physics class. Yeah. All right, thank you.